let yourself settle in for a moment. Find that comfortable position where your body can truly relax, where the weight of the day begins to lift from your shoulders like morning mist dissolving in sunlight. Take a slow, deep breath, feeling the air move through you, and as you exhale, let any tension drift away, carried off on an invisible current. Tonight, we're embarking on a journey through time itself, but not one that requires any effort from you. Just close your eyes if you'd like, or let them rest gently on a distant point, and allow the story to unfold around you like a gentle tide washing over warm sand. We're going to travel 5 billion years into the future, to a time so distant that it challenges everything we think we understand about permanence and change. But don't worry about grasping every detail or remembering every number. Let the words wash over you, painting pictures in your mind of cosmic landscapes that stretch beyond imagination. This is a story about transformation, about the inexorable march of time, and about how even the sun itself, that bright constant in our sky, is subject to the universe's great cycles of birth, life, and death. So, breathe, relax, and let's drift together into the depths of time, where the future of our cosmic home awaits. Before we begin this journey, I want to invite you to become part of our Science Pillow community. If you're finding comfort in these cosmic explorations, if these journeys through space and time help you unwind or drift off to sleep, please consider subscribing to the channel. Your subscription helps us continue creating these calming scientific adventures. And if you're enjoying tonight's voyage into the far future, a simple like on this video helps others discover these peaceful cosmic journeys. Thank you for being here, for sharing this moment with us as we explore the wonders of the universe together. Now, let's begin our journey 5 billion years into tomorrow. The journey begins 5 billion years hence. 5 billion years. Let that number settle in your mind for a moment, though in truth, it's a span of time so vast that our human brains, evolved to track days and seasons and lifetimes, struggle to give it any meaningful shape. 5 billion is a 5 followed by 9 zeros. 5 billion. It's not just a large number, it's a number that represents an almost incomprehensible gulf of time. To put this in perspective, consider that all of recorded human history, from the first cuneiform tablets pressed into Mesopotamian clay to this very moment, spans only about 5,000 years. That's a mere 1/1,000,000th of the journey we're about to take. If you could compress 5 billion years into a single calendar year, all of human civilization, from the agricultural revolution to the space age, would occupy only the last third of a second before midnight on December 31st. Think about it another way. The dinosaurs roamed the Earth until about 66 million years ago, when an asteroid strike brought their age to an abrupt end. That event, so ancient it seems to exist in a realm of pure mythology, happened only 1/75th of the way back to our starting point for tonight's journey. If we were to walk backward through time at a pace of 1 year per step, we'd have to walk more than 95 million miles to reach our destination, circling the Earth's equator nearly 4,000 times. 5 billion years ago, there was no Earth. There was no sun. There was only a vast cloud of gas and dust drifting through the Milky Way, a nebula that would eventually collapse under its own gravity to birth our solar system. The atoms in your body, the carbon and oxygen and nitrogen and iron, were floating free in that ancient cloud, having been forged in the hearts of even more ancient stars that had lived and died before our sun ever ignited. Now, Imagine traveling the same distance into the future. What would we find? What cosmic transformations await our solar system, our galaxy, our universe? This is the question that draws us forward tonight, into a future so distant that the earth beneath our feet, the solid ground that seems so permanent, will be long gone, consumed by the very star that gave it life. The journey ahead is not one of darkness and destruction alone, though there will be endings along the way. It's a journey that reveals the grand cycles of the cosmos, the way the universe continually transforms itself, breaking down old structures to build new ones. It's a reminder that change is the only constant, that even on the largest scales imaginable, nothing remains forever as it is. As we step forward into this deep future, the first thing we'd notice is that the sky above us looks different. The constellations we know, those patterns of stars that have guided human navigation and storytelling for thousands of years, have shifted. Stars move through space, orbiting the galactic center at different speeds and in different directions. Over 5 billion years, these motions have completely rearranged the night sky. The Big Dipper is no longer recognizable. Orion has scattered. New patterns have emerged from stars we can barely see today. But the most dramatic change, the transformation that dominates everything else, is happening directly overhead. The Sun, that familiar yellow disk that has illuminated Earth for billions of years, is dying. Or rather, it's beginning the final act of its stellar life, a transformation as inevitable as it is spectacular. This is where our journey truly begins, with the death of our star. The dying Sun, Earth's final chapter. The Sun is not eternal. This simple statement, while obvious to anyone with even a passing knowledge of astronomy, carries profound implications. The star that has nurtured life on Earth for more than 4 billion years, that has remained remarkably stable throughout the rise and fall of countless species, is a temporary phenomenon, a phase in an ongoing cosmic story. Currently, the Sun is about 4.6 billion years old, placing it roughly halfway through its main sequence lifetime. For the past 4.5 billion years, it has been steadily converting hydrogen into helium in its core through nuclear fusion, a process that releases tremendous amounts of energy. This energy pushes outward, counterbalancing the inward pull of gravity, maintaining the Sun in a stable equilibrium. It's a delicate balance, one that has held steady for eons. But nothing lasts forever. The Sun has been slowly brightening throughout its lifetime, increasing its luminosity by about 10% every billion years. This gradual brightening, imperceptible on human timescales, has profound long-term consequences. In roughly 1 billion years from now, well before our 5 billion year destination, this increased brightness will trigger a runaway greenhouse effect on Earth. The mechanism is both simple and devastating. As the Sun grows brighter, it pumps more energy into Earth's atmosphere. This extra heat causes the oceans to evaporate more quickly, putting more water vapor into the air. Water vapor is itself a greenhouse gas, trapping even more heat. This creates a feedback loop, a vicious cycle where more heat leads to more evaporation, which leads to more heat, which leads to more evaporation, until the process runs away completely. Within a few 100 million years of this process starting, Earth's oceans will have boiled away completely. The water molecules, broken apart by intense ultraviolet radiation in the upper atmosphere, will be split into hydrogen and oxygen. the lightweight hydrogen will escape into space, lost to Earth forever. The oxygen will likely react with rocks on the surface, becoming locked away in mineral compounds. What remains is a hellish, Venus-like world, with surface temperatures hot enough to melt lead, shrouded in thick clouds of steam and carbon dioxide. This is still a billion years in our future from now, but by the time we reach our 5-billion-year destination, this catastrophe is ancient history. Earth has been a dead world, devoid of liquid water and incapable of supporting life as we know it, for 4 billion years. Any life that once existed here either perished or found a way to leave, perhaps spreading to the outer solar system or to other stars entirely. But the Sun's transformation doesn't end with Earth's oceans boiling away. That's merely the beginning. As the Sun continues aging, the hydrogen fuel in its core gradually depletes. You might think this would cause the Sun to dim, to cool down as it runs out of fuel. But stellar evolution doesn't work that way. Instead, something far more dramatic occurs. When the hydrogen in the Sun's core is finally exhausted, fusion in the core will cease. Without the outward pressure from fusion reactions, the core will begin to contract under its own weight. As it contracts, it heats up, and this heat causes hydrogen in a shell surrounding the core to begin fusing. This shell burning is actually more energetic than the core burning that preceded it. The increased energy output causes the Sun's outer layers to expand dramatically. This is the beginning of the red giant phase, the most spectacular transformation in the Sun's life cycle. Over the course of several million years, the Sun will swell to enormous proportions. Its surface will cool as it expands, causing it to glow with a reddish hue rather than its current yellow-white. But its total energy output will increase significantly. The Sun will become a red giant, a bloated, dying star struggling through the final chapters of its existence. Just how large will the Sun become? Current models suggest that at its maximum size, the red giant Sun will expand to a radius of approximately 1 astronomical unit. An astronomical unit, or AU, is the current distance between Earth and the Sun, about 93 million miles or 150 million kilometers. In other words, the Sun's surface will reach all the way out to where Earth's orbit is now. This raises one of the most haunting questions in planetary science. Will Earth survive? For many years, astronomers assumed the answer was no. If the Sun expands to Earth's current orbital distance, our planet would find itself inside the Sun's outer atmosphere, dragged inward by friction with the tenuous solar gases. It would spiral into the Sun's depths and be vaporized, ending its existence in a final blaze of destruction. However, more recent calculations have complicated this picture. As the Sun expands and loses mass through powerful stellar winds, its gravitational grip on the planets will weaken. The planets' orbits will expand outward in response, moving to greater distances from the Sun. Some calculations suggest that Earth's orbit might expand by as much as 50%, potentially moving it just beyond the reach of the expanding Sun's atmosphere. But even in the most optimistic scenarios, Earth's survival is far from certain. The calculations are sensitive to many factors: the exact rate at which the Sun loses mass, the strength of the stellar winds, the complex interactions between Earth's orbit and the Sun's expanding envelope. Some models predict Earth will just barely escape engulfment, while others show it falling into the Sun by a relatively small margin. Klaus Peter Schroeder and Robert Smith, Astronomers who performed detailed calculations of Earth's fate concluded in their 2006 paper that Earth will not survive. According to their models, the ice-T Sun will begin its most rapid expansion phase about 7.59 billion years from now. At that point, even accounting for the outward migration of Earth's orbit due to the Sun's mass loss, our planet will find itself inside the Sun's atmosphere, just before the star reaches its maximum size. Once inside the solar atmosphere, Earth's fate is sealed. Friction with the surrounding gas will cause its orbit to decay. It will spiral inward over the course of perhaps a few 100,000 years, a blink of an eye in cosmic terms. As it descends into deeper, hotter layers of the Sun, Earth will heat up catastrophically. Its surface will melt, its crust will disintegrate, and eventually the entire planet will vaporize, its atoms dispersed into the solar winds, scattered across the inner solar system like ashes from a cremation. This is the fate that likely awaits Earth 5 billion years hence, assuming our calculations are correct. But what about the other planets? What happens to them during the Sun's death throes? Mercury and Venus, the two planets closer to the Sun than Earth, almost certainly will be engulfed. There's no scenario in which they escape. They orbit too close to the Sun, and even with orbital expansion, they'll find themselves deep within the red giant's atmosphere. Mercury will go first, swallowed when the Sun is still in the early stages of its expansion. Venus will follow soon after. Both will spiral inward and be destroyed, adding their mass to the Sun's outer layers. Mars, farther out than Earth, has a better chance. It might just barely escape engulfment, though it too will experience dramatic changes. The red giant Sun will bathe Mars in intense heat and radiation. If any ice remains in the Martian soil or at the poles, it will sublimate into the thin atmosphere. For a brief time, geologically speaking, Mars might even become warmer, though still probably not warm enough to be habitable in any conventional sense. The outer planets, Jupiter, Saturn, Uranus, and Neptune, will fare better. They orbit far enough from the Sun that even at its maximum expansion, they'll remain outside its atmosphere. However, they too will feel the effects of the dying Sun. The intense radiation will heat up their atmospheres, potentially causing some atmospheric loss, particularly for the ice giants Uranus and Neptune. Jupiter and Saturn, being more massive, will likely retain most of their atmospheres, though they'll be heated and energized by the increased solar output. Jupiter's magnificent storms, including the Great Red Spot if it still exists, will become even more energetic as the giant planet absorbs more heat from the expanded Sun. The cloud bands that stripe Jupiter's face will churn more violently, driven by increased temperature differences between the warmed upper atmosphere and the cooler depths below. Lightning storms in Jupiter's clouds, already the most powerful in the solar system, will become even more spectacular, flashing with energies that dwarf anything Earth has ever experienced. Saturn's beautiful rings, those delicate structures of ice and rock that have encircled the planet for perhaps only a few 100 million years, might not survive this transition. The increased heat from the red giant Sun could sublimate the ice in the rings, causing them to gradually dissipate into space. Alternatively, the rings might already be gone by this point due to other processes. They are remarkably fragile structures on cosmic timescales, and Saturn might have lost them long before the Sun reaches its red giant phase. Uranus and Neptune, the ice giants, will undergo perhaps the most dramatic transformation of the outer planets. Currently, frigid worlds with temperatures hovering around 50 to 70 Kelvin at their cloud tops, they'll warm substantially as the sun's luminosity increases. Their thick atmospheres of hydrogen, helium, and methane will heat up, driving powerful winds and weather systems. The methane in their atmospheres might begin to break down under the increased ultraviolet radiation, changing the blue-green color that characterizes these worlds today. But the most fascinating changes will occur on the moons of these giant planets. Our solar system hosts over 200 known moons, and many of them could experience dramatic transformations during the Sun's red giant phase. Europa, Jupiter's fourth largest moon, is one of the most intriguing bodies in the solar system. Beneath its cracked, icy surface lies a global ocean of liquid water, kept liquid by tidal heating from Jupiter's immense gravity. This ocean, perhaps 100 kilometers deep, might already harbor microbial life, sustained by chemical energy from hydrothermal vents on the ocean floor, much like certain ecosystems in Earth's deep oceans. When the Sun becomes a red giant, Europa's ice shell will melt. For the first time in billions of years, this hidden ocean will be exposed to open space. Liquid water will exist on Europa's surface, creating perhaps the most Earth-like environment in the solar system during this era. The surface will be warmer than it has ever been, possibly reaching temperatures where complex chemistry could occur rapidly. If life already exists in Europa's subsurface ocean, this could be its moment to flourish and diversify. With energy from both the sun and tidal heating, with nutrients from the rocky seafloor, and with liquid water under moderate temperatures, Europa could potentially develop a rich biosphere during this window. Photosynthetic organisms might evolve in the surface waters, creating Europa's first oxygen-rich atmosphere. Complex, multicellular life could develop in the newly accessible habitats. This renaissance would be temporary, lasting perhaps a few 100 million years at most. Once the Sun contracts to a white dwarf, Europa will freeze again, its brief moment of habitability ending as the solar heat source diminishes. But a few 100 million years is a long time in evolutionary terms. On Earth, it took roughly the same span of time for life to evolve from simple multicellular organisms to the incredible diversity of the Cambrian explosion. Europa's brief warm period could see similar evolutionary leaps. Ganymede, Jupiter's largest moon and the largest moon in the entire solar system, might undergo similar changes. Ganymede also appears to have a subsurface ocean, though it's buried deeper beneath ice and rock than Europa's ocean. When the outer ice melts during the red giant phase, Ganymede too might have surface liquid water, creating another potential refuge for life. Saturn's moon Titan presents an even more exotic possibility. Titan is the only moon in the solar system with a thick atmosphere, denser than Earth's, composed primarily of nitrogen with a few percent methane. Its surface, currently at a frigid 94 Kelvin, is dotted with lakes and seas of liquid methane and ethane. It's a world of organic chemistry, where complex carbon-based molecules form in the atmosphere and rain down onto the surface. When the Sun becomes a red giant, Titan will warm dramatically. The methane and ethane lakes will evaporate, creating an even thicker atmosphere. More importantly, the temperature might rise high enough for liquid water to exist on Titan's surface, perhaps in the form of water-ammonia mixtures that remain liquid at temperatures well below water's normal freezing point. Some scientists have speculated that this could create a truly unique environment. a world with both organic chemistry, from the existing hydrocarbons, and liquid water, the two key ingredients for life as we know it. Titan, during the red giant phase, might be one of the most chemically interesting places in the solar system, a laboratory for studying how life might emerge, or how existing microbial life might interact with this unusual chemistry. Enceladus, another of Saturn's moons, might also see dramatic changes. This small moon currently has geysers erupting from its south polar region, shooting water vapor and ice particles into space. These geysers hint at a subsurface ocean, kept liquid by tidal heating. When the sun's radiation intensifies, Enceladus's ice shell might thin or even melt entirely, creating another small ocean world in the outer solar system. Even distant bodies in the Kuiper Belt, the region beyond Neptune filled with icy bodies left over from the solar system's formation, will feel the effects of the red giant sun. Pluto and its moon Charon, currently frozen at temperatures around 40 Kelvin, will warm up. Pluto's thin atmosphere of nitrogen, which currently freezes onto the surface during most of its orbit, might become permanent and even thicker. Water ice beneath Pluto's surface might partially melt, creating subsurface liquid layers. Some scientists have speculated that if any form of conscious life were to exist in the solar system, during this era, perhaps having migrated from an earlier Earth or Mars, they might move outward as the inner solar system becomes uninhabitable. They might establish colonies on Europa or Titan during their brief warm periods, enjoying this Indian summer of the solar system before the sun's energy output drops too low to sustain liquid water anywhere in the system. It's a poignant image. The last outposts of solar system civilization, huddled around dim red dwarf stars or on warming moons in the outer solar system, watching the sun die, knowing that this brief window of habitability will close in a few 100 million years. They would face a choice: adapt to the coming cold, find ways to generate their own heat and energy, or leave the solar system entirely for younger, more vigorous stars. But let's return to the sun itself. The red giant phase, dramatic as it is only temporary. After perhaps a few 100 million years as a red giant, the sun will have lost a significant fraction of its mass to stellar winds. The calculations suggest it might lose 25 to 30% of its total mass, blowing this material out into space in a slowly expanding shell of gas. Meanwhile, deep in the sun's core, another transformation is taking place. The core, now composed primarily of helium, continues to contract and heat up under its own weight. Eventually, it becomes hot enough, around 100 million degrees Celsius, to ignite helium fusion. In a process called the helium flash, the core suddenly begins fusing helium into carbon and oxygen. This flash releases enormous amounts of energy, but it's absorbed by the surrounding stellar material, so it doesn't blow the star apart. After the helium flash, the sun settles into a new, brief equilibrium, burning helium in its core and hydrogen in a shell around the core. But this phase lasts only a fraction of the time that the sun spent on the main sequence. The sun burns through its helium fuel in perhaps 100 million years, a mere eye blink compared to the 10 billion years it spends burning hydrogen. When the helium is exhausted, the sun faces a crisis. It doesn't have enough mass to ignite the carbon and oxygen in its core. Heavier elements require higher temperatures to fuse, and the sun simply can't get hot enough. More massive stars can continue fusing carbon into neon, neon into magnesium, and so on up the periodic table. But the sun reaches the end of its fusion road with carbon and oxygen, Without fusion to support it, the core contracts one final time. The outer layers of the Sun, no longer supported by energy from below, begin to drift away. The Sun sheds its outer envelope in a series of pulses, each one pushing more material outward. These expanding shells of gas, lit from within by the hot stellar core, create what astronomers call a planetary nebula. The name is misleading. It has nothing to do with planets, but it describes the appearance. A beautiful, glowing shell or ring of gas expanding into space. At the center of this planetary nebula sits what's left of the Sun's core, a white dwarf. This object, roughly the size of Earth but containing about half the Sun's original mass, is one of the strangest objects in the universe. It's not burning fuel anymore. It's not generating energy through fusion or any other nuclear process. It's simply a hot, dense ball of carbon and oxygen, supported against gravitational collapse not by thermal pressure but by quantum mechanical effects, specifically electron degeneracy pressure. A white dwarf is so dense that a teaspoon of its material would weigh several tons on Earth. But despite this incredible density, it's remarkably stable. Once formed, a white dwarf will simply sit there, slowly radiating away its stored thermal energy over billions upon billions of years. It will cool from white-hot to yellow to red to, eventually, a theoretical black dwarf, a cold, dark stellar remnant that emits no light at all. However, the universe isn't old enough yet for any black dwarfs to exist. Even the oldest white dwarfs in the galaxy are still glowing faintly. The cooling process takes longer than the current age of the universe. But in our 5-billion-year future, the white dwarf that was once our Sun will have cooled significantly, probably down to a dull red glow, emitting just a tiny fraction of its former light. The Andromeda collision, a cosmic dance. While the Sun has been dying and transforming, something else remarkable has been happening on a much larger scale. Our entire galaxy, the Milky Way, has been engaged in a slow-motion cosmic collision with our nearest large galactic neighbor, Andromeda. The Andromeda Galaxy, also known as Messier 31 or M31, is currently about 2.5 million light-years away from us. On a clear, dark night, far from city lights, you can actually see it with your naked eyes as a faint, fuzzy smudge in the constellation Andromeda. What you're seeing is the combined light of roughly 1 trillion stars, an entire galaxy comparable in size to our own Milky Way. But Andromeda isn't staying put. It's moving toward us, approaching at a speed of about 110 kilometers per second, or roughly 68 miles per second. This might sound alarmingly fast, and indeed, by terrestrial standards it is, but on cosmic scales, it's a leisurely pace. Even at this speed, it takes Andromeda a long time to cover the vast distance between our galaxies. For many years, astronomers believed with reasonable certainty that Andromeda and the Milky Way would collide. In 2012, scientists using the Hubble Space Telescope made precise measurements of stars in Andromeda, tracking their positions over several years. By combining these position measurements with knowledge of how fast Andromeda is approaching, determined from its Doppler shift, they were able to calculate Andromeda's trajectory through space. Their conclusion was that a direct collision was virtually certain, likely to occur in about 4 to 4.5 billion years. However, more recent research published in 2025 has complicated this picture. When astronomers included the gravitational effects of other nearby galaxies, particularly the Large Magellanic Cloud and the Triangulum Galaxy, In their calculations, they found that the eye's probability of a collision is much lower than previously thought. According to this new analysis, there's only about a 50% chance that the Milky Way and Andromeda will collide within the next 10 billion years. For our thought experiment tonight, though, let's assume that the collision does occur, as many earlier studies predicted. What would this cosmic encounter look like? What happens when two giant spiral galaxies, each containing hundreds of billions of stars, merge together? The first thing to understand is that when we say galaxies collide, we're not talking about stars smashing into each other like cars in a traffic accident. Galaxies are mostly empty space. The distances between stars within a galaxy are vast compared to the sizes of the stars themselves. To get a sense of the scale, imagine the Sun as a ping-pong ball. On this scale, the nearest star, Proxima Centauri, would be another ping-pong ball about 1,100 kilometers away. The space between is empty. When two galaxies merge, the stars pass by each other like ghosts, rarely, if ever, coming close to collision. The probability of any two stars actually hitting each other during a galactic collision is astronomically small. So small, in fact, that we can effectively ignore it. In all likelihood, not a single stellar collision would occur during the Milky Way-Andromeda merger. But even though the stars don't collide, the galaxies profoundly affect each other. Gravity reaches across the empty space between stars, and when two galaxies come together, every star in each galaxy feels the gravitational pull of every star in the other galaxy, plus the pull of all the dark matter that surrounds and interpenetrates both galaxies. The result is a magnificent cosmic dance. As Andromeda approaches the Milky Way, its gravitational field begins to deform our galaxy. The outer regions of both galaxies stretch toward each other, creating tidal arms. Long streams of stars pulled out from the main galactic disks. These tidal tails can extend for hundreds of thousands of light years, reaching out across the void like cosmic fingers. The first close approach between the galaxies would occur around 4 billion years from now, roughly a billion years before our 5 billion year mark. At this point, Andromeda would dominate the night sky. No longer a faint smudge, but a spectacular sight stretching across the heavens. To an observer on a planet in either galaxy, assuming any planets with observers still exist, it would be like watching two celestial hurricanes approaching each other in slow motion. As the galaxies make their first pass, they distort each other dramatically. The beautiful spiral structures that both galaxies currently possess would be disrupted. Star-forming regions would light up across both galaxies as clouds of gas and dust collide. Unlike stars, gas clouds are large and diffuse enough to actually run into each other. These collisions compress the gas, triggering bursts of new star formation. The sky would light up with brilliant young blue stars and the pink glow of ionized hydrogen gas. The visual spectacle would be unlike anything we can observe in our current universe from our vantage point. Imagine standing on a hypothetical planet orbiting a star in one of these colliding galaxies. The sky would be ablaze with newborn stars, brilliant blue giants that burn with the intensity of thousands of suns. These massive stars are short-lived, burning through their fuel in just a few million years before exploding as supernovae. The night sky would be punctuated by supernova explosions, each one briefly outshining entire sections of the galaxy. Between the bursts of star formation, you would see the twisted, distorted arms of both galaxies stretching across the sky. Long tidal streamers of stars, pulled out from the galactic disks by gravitational forces, would curve gracefully through space like cosmic rivers. Some of these streamers would loop back and fall into one of the galaxies. Others would be flung out into intergalactic space, their stars destined to wander in isolation between galaxy clusters. The gas clouds colliding within the galaxies would create shock fronts, regions where the gas is compressed and heated to millions of degrees. These shock fronts would glow in X-rays, invisible to human eyes but brilliant to any instruments sensitive to high-energy radiation. The collision would pump enormous amounts of energy into the interstellar medium, heating gas that had been cold and dark for billions of years. Some of this hot gas would be driven out of the galaxies entirely, blown away by the combined pressure of stellar winds from thousands of massive stars and the explosive force of countless supernovae. This galactic wind would carry heavy elements, carbon, oxygen, nitrogen, iron, out into intergalactic space, enriching the thin gas that fills the voids between galaxies. Future generations of galaxies forming from this enriched gas would have higher metallicities, better able to form rocky planets and, potentially, life. But the galaxies don't merge on this first pass. Instead, having traded momentum and energy through their gravitational interactions, they swing past each other and begin to separate again. However, they're now gravitationally bound to each other, like two dancers who have locked arms. They can't escape. Gravity draws them back together for a second pass, and then a third. Each passage deforms the galaxies further. The neat spiral arms become increasingly scrambled. Stars are flung into new orbits, some thrown far from their original positions. Some stars gain enough energy to escape the galaxy entirely, becoming hypervelocity stars that shoot through intergalactic space at speeds of hundreds or even thousands of kilometers per second. These stellar outcasts will spend the rest of their lives traveling between galaxies, solitary wanderers in the cosmic void. With each pass, the galaxies lose energy and momentum to the surrounding space through a process called dynamical friction, involving their dark matter halos. This process, similar to how a spacecraft uses atmospheric drag to slow down, causes the galaxy's orbits to decay. They spiral closer together with each passage, their separation decreasing from millions of light years to hundreds of thousands to, eventually, just tens of thousands of light years. During this dance, the central regions of both galaxies, the dense bulges where stars pack closely together, begin to merge. Stars from both galaxies intermingle, their orbits becoming hopelessly tangled. The distinctive rotation that characterizes spiral galaxies begins to break down. Instead of stars moving in ordered circular orbits around the galactic center, they follow chaotic, randomized paths. The galaxies are transitioning from ordered, rotating disks to disordered, pressure-supported ellipticals. After, perhaps, 2 billion years of this cosmic dance, the galaxies finally merge completely. Their central regions combine, and their supermassive black holes, the 4 million solar mass giant at the center of the Milky Way and Andromeda's own central black hole, thought to be somewhere between 10 and 100 times more massive, spiral in toward each other. This final merger of the supermassive black holes is itself a spectacular event, though it would be invisible to any electromagnetic telescope. As the black holes orbit each other, getting closer and closer, they generate powerful gravitational waves. ripples in the fabric of space-time itself that propagate outward at the speed of light. These waves carry energy away from the system, causing the black hole's orbit to decay even faster. Einstein's general theory of relativity predicts these gravitational waves, and we've now directly detected them from merging black holes using instruments like LIGO and Virgo. But those detections were of stellar mass black holes, each containing just a few dozen times the Sun's mass. The merger of supermassive black holes, like those at the centers of the Milky Way and Andromeda, would generate gravitational waves millions of times more powerful. In the final moments before merger, as the two black holes whip around each other at a significant fraction of the speed of light, separated by a distance less than the size of our solar system, they would emit a crescendo of gravitational waves. Any gravitational wave detector in the nearby universe would pick up this signal, watching as the frequency of the waves increased, rising in pitch like a cosmic siren, before suddenly cutting off as the black holes merged into one. The combined black hole would initially be distorted, spinning and vibrating like a struck bell. It would emit more gravitational waves as it rings down to a stable, rotating state. The entire process, from the point where the black holes get close enough to merge rapidly to the final stable black hole, might take just a few hours or days, a blink of an eye compared to the billions of years it took the galaxies to collide. The resulting black hole would contain the combined mass of both parent black holes, minus whatever mass was radiated away as gravitational wave energy during the merger. If the Milky Way's black hole has 4 million solar masses and Andromeda's has 40 million, a reasonable estimate, the merged black hole would have roughly 44 million solar masses, making it one of the more massive black holes in the local universe. This supermassive black hole would sit at the heart of Andromeda, the new merged galaxy. It would likely go through periods of intense activity, episodes where infalling gas causes it to shine brightly as a quasar or active galactic nucleus. But these active periods would be temporary, lasting only as long as there's gas available to fall into the black hole. Eventually, the black hole would settle into a quiet state, lurking in the galactic center, its presence felt only through its gravitational influence on nearby stars. The resulting merged galaxy, playfully nicknamed Milkomeda or Milkdromeda by astronomers, will look nothing like its parent galaxies. Gone are the graceful spiral arms, the flat rotating disks. In their place is a giant elliptical galaxy, a roughly football-shaped swarm of stars with no particular structure or rotation pattern. The stars follow random, chaotic orbits around the galactic center, creating a smooth, featureless glow. This is a common outcome for major galaxy mergers. When two spiral galaxies of similar size collide, they tend to destroy each other's spiral structures and create ellipticals. We see many such elliptical galaxies in the universe today, testament to ancient collisions that occurred billions of years ago. What about our Sun during all of this? If it still exists as a white dwarf at this point, and it probably does, since the collision timeline overlaps with the end of the Sun's red giant phase, it will be swept along with all the other stars in the Milky Way. Its position in the merged galaxy will likely be quite different from its current position in the Milky Way. Computer simulations of the Milky Way-Andromeda merger suggest that there's about a 50% chance that the Sun, or its white dwarf remnant, will end up at a distance 2 to 3 times farther from the galactic center than it is now. There's also roughly a 12% chance that the Sun could be flung entirely out of the merged galaxy, ejected into intergalactic space by a close gravitational encounter with other stars during the chaotic merger process. If this happens, the Sun's white dwarf remnant would find itself drifting through the vast emptiness between galaxies, slowly cooling in isolation. Any planets that might still orbit it, perhaps some of the outer planets like Jupiter or Saturn, would be carried along into this cosmic exile. The night sky from such a planet would be profoundly different. No more Milky Way stretching across the heavens, just the merged Milkomeda galaxy as a distant smudge of light, along with other galaxies scattered across the cosmic void. For any hypothetical observers 5 billion years hence, assuming there are any, the formation of Milkomeda would mark the end of an era. The Milky Way as we know it, the galaxy that has been humanity's home for all of our existence, would be gone, its stars scattered and redistributed in a new cosmic structure. But the universe would continue, indifferent to our parochial concerns about galactic identity, the universe at 5 billion years. While these dramatic events have been unfolding in our local cosmic neighborhood, the sun dying, the planets being destroyed or scattered, the Milky Way colliding with Andromeda, the broader universe has been evolving as well. Let's zoom out and examine the state of the cosmos 5 billion years in the future. The most important thing to understand about the universe at this time is that it's significantly larger than it is today. The universe has been expanding since the Big Bang, and not only expanding but expanding at an accelerating rate. This acceleration, discovered in the late 1990s, came as a complete surprise to astronomers. Before this discovery, scientists assumed that the expansion of the universe, set in motion by the Big Bang, must be slowing down. After all, gravity should be pulling everything back together, working against the expansion. They debated whether there was enough matter in the universe for gravity to eventually halt and reverse the expansion, leading to a big crunch, or whether the expansion would continue forever but gradually slow down. What they didn't expect was that the expansion is speeding up. This acceleration is attributed to something called dark energy, one of the greatest mysteries in modern physics. Dark energy appears to be a property of space itself, a kind of anti-gravity that pushes things apart rather than pulling them together. The more space there is, the more dark energy there is, creating a feedback loop that drives ever faster expansion. We don't really know what dark energy is. It might be a cosmological constant, an inherent property of the vacuum of space that Einstein actually predicted in his equations, though he later rejected the idea, calling it his biggest blunder. Or it might be something more exotic, a dynamic field that changes over time. Some very recent observations from the Dark Energy Spectroscopic Instrument, DESI, have hinted that dark energy might not be constant after all, that it might be evolving in ways we don't yet understand. But these results are still preliminary and controversial. Regardless of its true nature, dark energy has profound implications for the future of the universe. It means that the expansion will continue indefinitely, and indeed will accelerate. The space between galaxy clusters will grow larger and larger, stretching out the cosmic web that connects them. 5 billion years from now, this effect will have become quite noticeable. Many galaxies that we can see today will have moved farther away, their light shifted toward the red end of the spectrum by the expansion of space. Some of the most distant galaxies visible to our current telescopes will have receded so far that they'll no longer be detectable, having crossed beyond what's called the cosmic event horizon. This cosmic event horizon is an important concept. It's similar in some ways to the event horizon of a black hole, but instead of being a boundary around a compact object, it's a sphere expanding around us. Galaxies beyond this horizon are receding from us faster than the speed of light. Not because they're moving through space faster than light, which would violate relativity, but because space itself is expanding so rapidly between us and them. Light from these distant galaxies can never reach us, no matter how long we wait. They're not just too far away, they're becoming unreachable. Over time, more and more galaxies will cross this horizon and disappear from our view. The observable universe, paradoxically, will contain fewer and fewer galaxies as time goes on, even as the total universe presumably continues to contain the same number, or more if you count newly formed smaller galaxies. However, 5 billion years isn't long enough for this effect to be dramatic. Most of the galaxies we can see today will still be visible, though many will have shifted significantly in the sky as the cosmic web evolves and restructures itself. Galaxy clusters will have merged with other clusters, forming even larger structures. The local group, our small collection of galaxies including the Milky Way, Andromeda, and about 50 smaller galaxies, will likely have already merged into Andromeda and absorbed most of its smaller members. On the larger scale, the Virgo supercluster, the vast structure of which our local group is a tiny part, will have continued to evolve. Some of its member clusters will have merged. Others will have been pulled away by the expansion of space. The cosmic web of filaments and voids will have shifted and changed, but it will still be recognizable as fundamentally the same structure we see today. Star formation across the universe will still be ongoing 5 billion years from now, though it will have declined from its peak. The universe produced stars most rapidly when it was about 2 to 3 billion years old, roughly 10 to 11 billion years ago from our present day. Since then, the rate has been declining steadily. Galaxies are running low on the raw material for star formation, cold gas clouds. Much of the gas has already been incorporated into stars or heated too much to collapse and form new stars. Still, 5 billion years from now isn't so far in the future that star formation has ceased entirely. New stars are still being born, particularly in galaxies that have recently undergone mergers, like Andromeda, or in gas-rich dwarf galaxies. These newborn stars will be different in composition from the oldest stars in the universe, enriched with heavier elements created in earlier generations of stars. But they'll still be recognizably stars, balls of hydrogen and helium undergoing nuclear fusion. The universe will be about 18.8 billion years old at our 5 billion year waypoint. This is still relatively young on cosmic timescales. The oldest stars that exist today, low-mass red dwarfs, will still be on the main sequence, still fusing hydrogen into helium in their cores. These stars have lifetimes measured in trillions of years, so from their perspective, 5 billion years is barely any time at all. The cosmic microwave background radiation, the afterglow of the Big Bang, will still be detectable, though it will have cooled further due to the expansion of space. Currently, at a temperature of about 2.7 Kelvin, 2.7 degrees above absolute zero, it will have cooled to perhaps 2.5 Kelvin or thereabouts. Advanced civilizations, if any exist, would still be able to study it and extract information about the early universe from its patterns. Dark matter, the invisible substance that makes up about 85% of all matter in the universe, will still be exactly where it was, forming the gravitational scaffolding around which galaxies cluster. Dark matter doesn't emit light, doesn't absorb light and doesn't interact with normal matter except through gravity, so it's largely immune to the aging process that affects stars and galaxies. The dark matter halos that surround galaxies will have evolved somewhat, growing through mergers and the accumulation of more dark matter. But they'll still be performing their crucial role of holding galaxies together. In short, the universe at 5 billion years will be recognizably the same universe we inhabit today, just older, larger, and somewhat different in detail. It's not yet old enough for the truly dramatic changes that await in the deep future. For those, we need to look much, much farther ahead. The Stelliferous Era Continues. The period we're in now, and that the universe will still be in 5 billion years from now, is called the Stelliferous Era, the Age of Stars. This epoch, which began a few 100 million years after the Big Bang when the first stars ignited, is characterized by the universe being lit up by stellar light. Stars are the dominant sources of energy, and they're responsible for most of the interesting things that happen in the cosmos. But the Stelliferous Era won't last forever. Eventually, the universe will run out of the raw materials needed to make new stars, and the existing stars will burn out. When the last star finally fades away, the universe will enter a new epoch, darker and colder, fundamentally different from the bright cosmos we know today. However, that transition is still very far in the future. 5 billion years from now, the Stelliferous Era is still going strong. Stars are still being born, albeit at a slower rate than in the past. To understand what's happening in this era and what will happen in the distant future, we need to understand how stars are born and how they die. Stars form from clouds of gas and dust called molecular clouds. These clouds, some of them hundreds of light years across and containing enough material to make millions of stars, float through the galaxy. They're cold and dark, barely warmer than the frigid cosmic background temperature. But they're not entirely stable. Turbulence within the cloud, the shock wave from a nearby supernova, or the gravitational influence of a passing star can cause parts of the cloud to start contracting. Once a region begins to contract, gravity takes over. As the gas collapses inward, it heats up due to compression. If the collapsing region is massive enough and can shed heat fast enough to avoid being disrupted by the rising temperature and pressure, it will continue collapsing until the core becomes hot enough, about 10 million degrees Celsius, to ignite hydrogen fusion. At this point, a star is born. The mass of the forming star determines its entire life story. High-mass stars, those with more than 8 times the Sun's mass, burn brilliantly and die young, exhausting their fuel in just a few million to a few 100 million years before exploding as supernovae. Stars like the Sun, with roughly 1 solar mass, burn for about 10 billion years. Low-mass red dwarfs, with just 10 to 50% of the Sun's mass, burn so slowly and efficiently that they can last for trillions of years. This relationship between mass and lifetime is crucial for understanding the future of the universe. The rate at which stars form depends on the availability of gas and dust. As time goes on, more and more of the galaxy's gas gets locked up in stars or blown out of the galaxy by stellar winds and supernova explosions. Less gas means fewer new stars. 5 billion years from now, the Milky Way, or rather, Andromeda, will have significantly less gas available for star formation than it does today. Some of this gas has been turned into stars. Some has been heated by supernova shocks and energetic radiation from massive stars, making it too hot to collapse and form new stars. Some has been enriched with heavy elements, changing its chemical composition and affecting how it cools and collapses. But star formation hasn't stopped entirely. In fact, the recent merger with Andromeda will have triggered a burst of new star formation. When the two galaxies collide, their gas clouds slam into each other, compressing the gas and triggering the collapse of many new stars. Andromeda is probably in the midst of this starburst, with brilliant young stars lighting up regions where gas clouds have collided. These young stars will be among the last massive stars to form in Andromeda. Once this burst of star formation dies down as the merger settles and the gas is exhausted or dispersed, the galaxy will produce mostly low-mass stars. The era of massive, brilliant stars is coming to an end. This is actually happening across the universe, not just in our local galaxy. The cosmic star formation rate peaked about 10 billion years ago and has been declining ever since. Studies suggest that only about 5% of all the stars that will ever exist in the universe have yet to be born. We're living in the late stages of the Stelliferous Era, when the universe's stellar productivity is already past its prime. But late stages, in cosmic terms, still means an enormously long time. Current models suggest that star formation will continue, at a declining rate, for another 1 to 100 trillion years. That's 1 to 100,000 billion years. A time span that makes 5 billion years seem like the blink of an eye. The stars that form later in this era will be different from those forming now. They'll be enriched with heavy elements from previous generations of stars. When the first stars formed, shortly after the Big Bang, the universe contained only hydrogen, helium, and tiny traces of lithium. All the heavier elements, carbon, nitrogen, oxygen, iron, gold, everything, has been made inside stars and dispersed by stellar winds and supernova explosions. Each new generation of stars incorporates these heavy elements, becoming more metal-rich in astronomical parlance. Astronomers call everything heavier than helium a metal, even though chemists would object to calling carbon or oxygen or nitrogen metals. These heavier elements affect how stars form and evolve. They make it easier for gas clouds to cool and collapse. They change the opacity of stellar atmospheres. They enable the formation of planets and, potentially, life. By 5 billion years from now, stars will be even more metal-rich than the Sun, containing a higher proportion of heavy elements. Any planets forming around these stars will also be richer in heavy elements, potentially creating Earth-like worlds with larger iron cores and different geological characteristics than our Earth. The dominant stars in the universe 5 billion years from now, as they are today and will be for trillions of years to come, are red dwarfs. These small, cool stars make up about 75% of all stars in the Milky Way. They're so faint that not a single red dwarf is visible to the naked eye from Earth, despite there being billions of them in our galaxy. The nearest star to our Sun, Proxima Centauri, is a red dwarf, but it's too dim to see without a telescope. Red dwarfs are the universe's penny pinchers, burning their hydrogen fuel with extreme efficiency. They're fully convective, meaning their interiors are constantly mixing, bringing fresh hydrogen from their outer layers down to the core where fusion occurs. This allows them to burn essentially their entire supply of hydrogen, not just the hydrogen in the core like Sun-like stars do. As a result, red dwarfs can last for enormous periods of time. A red dwarf with 10% of the Sun's mass will burn for approximately 6 to 12 trillion years before exhausting its hydrogen fuel. That's hundreds of times longer than the current age of the universe. The smallest red dwarfs might last even longer. When a red dwarf finally does run out of hydrogen, its end is quite different from the Sun's dramatic red giant phase. Red dwarfs don't have enough mass to expand into red giants. Instead, they simply heat up and contract, becoming blue dwarfs for a time before finally running out of fuel and contracting into white dwarfs. This process takes so long that no red dwarf in the universe has yet completed it. The universe isn't old enough. These long-lived red dwarfs represent the universe's future. Long after the last massive stars have exploded as supernovae, long after stars like the Sun have swelled into red giants and collapsed into white dwarfs, red dwarfs will still be shining, steadily burning their hydrogen fuel, patiently waiting for their turn to fade. 5 billion years from now, most of the red dwarfs that exist today will still be on the main sequence, looking and behaving almost exactly as they do now. They'll have made a tiny dent in their fuel supply, perhaps burning through a fraction of a percent of their hydrogen, but otherwise they'll be unchanged. In the deep future, when the last conventional star finally winks out, it will probably be a red dwarf that held on the longest. The Stelliferous Era Continues. The period we're in now, and that the universe will still be in 5 billion years from now, is called the Stelliferous Era, the Age of Stars. This epoch, which began a few 100 million years after the Big Bang when the first stars ignited, is characterized by the universe being lit up by stellar light. Stars are the dominant sources of energy, and they're responsible for most of the interesting things that happen in the cosmos. But the Stelliferous Era won't last forever. Eventually, the universe will run out of the raw materials needed to make new stars, and the existing stars will burn out. When the last star finally fades away, the universe will enter a new epoch, darker and colder, fundamentally different from the bright cosmos we know today. However, that transition is still very far in the future. 5 billion years from now, the Stelliferous Era is still going strong. Stars are still being born, albeit at a slower rate than in the past. To understand what's happening in this era and what will happen in the distant future, we need to understand how stars are born and how they die. Stars form from clouds of gas and dust called molecular clouds. These clouds, some of them hundreds of light years across and containing enough material to make millions of stars, float through the galaxy. They're cold and dark, barely warmer than the frigid cosmic background temperature. But they're not entirely stable. Turbulence within the cloud, the shock wave from a nearby supernova, or the gravitational influence of a passing star can cause parts of the cloud to start contracting. Once a region begins to contract, gravity takes over. As the gas collapses inward, it heats up due to compression. If the collapsing region is massive enough and can shed heat fast enough to avoid being disrupted by the rising temperature and pressure, it will continue collapsing until the core becomes hot enough, about 10 million degrees Celsius, to ignite hydrogen fusion. At this point, a star is born. The mass of the forming star determines its entire life story. High-mass stars, those with more than 8 times the Sun's mass, burn brilliantly and die young, exhausting their fuel in just a few million to a few 100 million years before exploding as supernovae. Stars like the Sun, with roughly 1 solar mass, burn for about 10 billion years. Low-mass red dwarfs, with just 10 to 50% of the Sun's mass, burn so slowly and efficiently that they can last for trillions of years. This relationship between mass and lifetime is crucial for understanding the future of the universe. The rate at which stars form depends on the availability of gas and dust. As time goes on, more and more of the galaxy's gas gets locked up in stars or blown out of the galaxy by stellar winds and supernova explosions. Less gas means fewer new stars. 5 billion years from now, the Milky Way, or rather, Andromeda, will have significantly less gas available for star formation than it does today. Some of this gas has been turned into stars. Some has been heated by supernova shocks and energetic radiation from massive stars, making it too hot to collapse and form new stars. Some has been enriched with heavy elements, changing its chemical composition and affecting how it cools and collapses. But star formation hasn't stopped entirely. In fact, the recent merger with Andromeda will have triggered a burst of new star formation. When the two galaxies collide, their gas clouds slam into each other, compressing the gas and triggering the collapse of many new stars. Andromeda is probably in the midst of this starburst, with brilliant young stars lighting up regions where gas clouds have collided. These young stars will be among the last massive stars to form in Andromeda. Once this burst of star formation dies down as the merger settles and the gas is exhausted or dispersed, the galaxy will produce mostly low-mass stars. The era of massive, brilliant stars is coming to an end. This is actually happening across the universe, not just in our local galaxy. The cosmic star formation rate peaked about 10 billion years ago and has been declining ever since. Studies suggest that only about 5% of all the stars that will ever exist in the universe have yet to be born. We're living in the late stages of the Stelliferous Era, when the universe's stellar productivity is already past its prime. But late stages, in cosmic terms, still means an enormously long time. Current models suggest that star formation will continue, at a declining rate, for another 1 to 100 trillion years. That's 1 to 100,000 billion years. A time span that makes 5 billion years seem like the blink of an eye. The stars that form later in this era will be different from those forming now. They'll be enriched with heavy elements from previous generations of stars. When the first stars formed, shortly after the Big Bang, the universe contained only hydrogen, helium, and tiny traces of lithium. All the heavier elements, carbon, nitrogen, oxygen, iron, gold, everything, has been made inside stars and dispersed by stellar winds and supernova explosions. Each new generation of stars incorporates these heavy elements, becoming more metal-rich in astronomical parlance. Astronomers call everything heavier than helium a metal, even though chemists would object to calling carbon or oxygen or nitrogen metals. These heavier elements affect how stars form and evolve. They make it easier for gas clouds to cool and collapse. They change the opacity of stellar atmospheres. They enable the formation of planets and, potentially, life. By 5 billion years from now, stars will be even more metal-rich than the Sun, containing a higher proportion of heavy elements. Any planets forming around these stars will also be richer in heavy elements, potentially creating Earth-like worlds with larger iron cores and different geological characteristics than our Earth. The dominant stars in the universe 5 billion years from now, as they are today and will be for trillions of years to come, are red dwarfs. These small, cool stars make up about 75% of all stars in the Milky Way. They're so faint that not a single red dwarf is visible to the naked eye from Earth, despite there being billions of them in our galaxy. The nearest star to our Sun, Proxima Centauri, is a red dwarf, but it's too dim to see without a telescope. Red dwarfs are the universe's penny pinchers, burning their hydrogen fuel with extreme efficiency. They're fully convective, meaning their interiors are constantly mixing, bringing fresh hydrogen from their outer layers down to the core where fusion occurs. This allows them to burn essentially their entire supply of hydrogen, not just the hydrogen in the core like Sun-like stars do. As a result, red dwarfs can last for enormous periods of time. A red dwarf with 10% of the Sun's mass will burn for approximately 6 to 12 trillion years before exhausting its hydrogen fuel. That's hundreds of times longer than the current age of the universe. The smallest red dwarfs might last even longer. When a red dwarf finally does run out of hydrogen, its end is quite different from the Sun's dramatic red giant phase. Red dwarfs don't have enough mass to expand into red giants. Instead, they simply heat up and contract, becoming blue dwarfs for a time before finally running out of fuel and contracting into white dwarfs. This process takes so long that no red dwarf in the universe has yet completed it. The universe isn't old enough. These long-lived red dwarfs represent the universe's future. Long after the last massive stars have exploded as supernovae, long after stars like the Sun have swelled into red giants and collapsed into white dwarfs, red dwarfs will still be shining, steadily burning their hydrogen fuel, patiently waiting for their turn to fade. 5 billion years from now, most of the red dwarfs that exist today will still be on the main sequence, looking and behaving almost exactly as they do now. They'll have made a tiny dent in their fuel supply, perhaps burning through a fraction of a percent of their hydrogen, but otherwise they'll be unchanged. In the deep future, when the last conventional star finally winks out, it will probably be a red dwarf that held on the longest. The far, far future, beyond 5 billion years. Our journey has taken us 5 billion years into the future, a span of time that encompasses the death of our Sun and the collision of our galaxy with Andromeda. But 5 billion years, vast as it seems, is just a tiny step into the depths of cosmic time. If we want to truly understand the ultimate fate of the universe, we need to venture much, much farther into the future. Let's continue our journey, accelerating through time, watching as eons pass like hours. A billion years becomes a unit of time no more significant than a single year is to us. We're traveling into a future so distant that even geologic ages become mere moments. 10 billion years from now, about 5 billion years beyond our previous stopping point, the universe will be about 24 billion years old. The merged galaxy Andromeda will have settled into a steady state. Its burst of star formation from the merger long since ended. The supermassive black hole at its center, formed from the merger of the Milky Way's and Andromeda's central black holes, will have grown even larger by consuming gas and occasionally other stars that wander too close. The Triangulum galaxy, the third largest member of the local group, may have merged with Andromeda by this point, adding its 100 billion or so stars to the mix. Most of the smaller dwarf galaxies that orbit the major galaxies will have been absorbed as well. The local group will have been reduced to perhaps one large elliptical galaxy, plus a handful of very distant, very small dwarf galaxies that haven't yet been captured. The Sun's white dwarf remnant, if it survived the red giant phase and wasn't ejected from the galaxy, will have cooled significantly. After 10 billion years of radiating away its heat, it will be much dimmer and cooler than when it first formed. Any planets that still orbit it will be frozen, far colder than Pluto is today, receiving only the faintest warmth from their dying star. Now, let's jump much farther ahead. 100 billion years from now, the universe will have undergone a remarkable transformation. At this point, the accelerating expansion of space will have carried most galaxies beyond the cosmic event horizon. From any vantage point within Andromeda or any other galaxy, the sky will appear profoundly empty. A hypothetical astronomer in this distant era, looking out into space, would see only the stars of their own galaxy. All the other galaxies in the universe would have receded beyond visibility, carried away by the expansion of space. The cosmic microwave background, now stretched to enormously long radio wavelengths and cooled to a fraction of a degree above absolute zero, would be undetectable with any technology based on current physics. This astronomer would have no direct evidence that the universe is larger than their own galaxy. They might infer from theoretical considerations that there must be other galaxies out there somewhere, but they would have no way to observe them. The universe would appear to have shrunk down to a single island of stars surrounded by infinite darkness. The Virgo supercluster, of which Andromeda is a member, will have fully merged into a single megagalaxy by this point. This enormous structure, containing the mass of thousands of galaxies, will be gravitationally bound tightly enough that the expansion of space can't pull it apart. It will be a true island universe, isolated from all other galaxies by the ever-expanding void. This mega-galaxy would be a sight to behold if anyone were around to see it. Spanning perhaps 10 million light-years or more, it would be a diffuse swarm of hundreds of trillions of stars, most of them old and faint. At its center would be a supermassive black hole of truly staggering proportions, perhaps containing hundreds of billions or even a trillion times the mass of our Sun, grown fat from consuming gas and smaller black holes over the eons. The structure of this mega-galaxy would be quite different from the galaxies we see today. Modern elliptical galaxies, formed from galaxy mergers, show a relatively smooth distribution of stars with brightness decreasing toward the edges. But this mega-galaxy, formed from the merger of hundreds or thousands of individual galaxies, might show remnant structures, shells and streams of stars marking ancient merger events, like archaeological layers revealing the galaxy's history. Within this vast stellar city, the dynamics would be dominated by chance encounters between stars. Over timescales of trillions of years, nearly every star would have a close encounter with at least one other star. These encounters wouldn't typically result in collisions. Space is still mostly empty even in the densest regions, but they would alter stellar orbits, sending some stars on wider paths and others spiraling inward toward the central black hole. Star formation, meanwhile, will have declined dramatically. Most of the gas has been used up or heated too much to form stars. A few last pockets of cold gas might still collapse to form red dwarfs, but these occasions will be rare. The universe is transitioning from a cosmos dominated by bright, young stars to one dominated by old, dying stars and their remnants. The galaxy's outer regions would gradually evaporate as stars gain enough energy in random encounters to escape the galaxy's gravitational pull entirely. These ejected stars, cast out into the void between galaxies, would become wanderers, drifting through intergalactic space with no home. Over a period of perhaps 10 to the 20 years or so, half of the galaxy's stars might be lost this way, slowly bleeding away into the surrounding emptiness. Meanwhile, stars that lose energy in encounters would fall inward, adding to the dense core of the galaxy. This process, called core collapse, would concentrate more and more stars in the central regions, increasing the chance of further encounters and accelerating the process. Eventually, most of these core stars would fall into the central supermassive black hole, their mass adding to its already impressive bulk. Now, let's jump to 1 trillion years in the future. This is roughly 100 times the current age of the universe. At this point, according to current models, the last new stars will be forming. These final stars will almost certainly be low-mass red dwarfs, squeezing into existence from the very last remaining clouds of cold hydrogen gas. Once these clouds are exhausted, no more stars can form. The materials are gone. This is a significant milestone in cosmic history. For nearly 1 trillion years, ever since a few 100 million years after the Big Bang when the first stars ignited, the universe has been producing new stars. The rate has varied over time, peaking about 10 to 11 billion years ago and declining since then, but there have always been new stars being born somewhere. At the 1 trillion year mark, this comes to an end. The era of star formation closes. The sky will have grown darker. Most of the massive stars that existed earlier have long since exploded as supernovae, their cores collapsing to form neutron stars or black holes. Medium-mass stars like the Sun have all passed through their red giant phases and become white dwarfs, now cooling and dimming. Even some of the smaller stars are beginning to run out of fuel. The galaxy, or megagalaxy, is populated primarily by red dwarfs, white dwarfs, neutron stars, and black holes. The red dwarfs, faithful and long-lived, continue shining as they have for trillions of years. They're the last sources of starlight in a darkening universe. Around them, any planets that remain orbit in the cold and dark, occasionally illuminated by the dim reddish glow of their small suns. These planets, if any still exist, would be incredibly old by this point, having orbited their stars for 1 trillion years. Any geological activity they once had would have long since ceased. They would be cold, dead worlds, their surfaces covered in the accumulated dust and debris of 1 trillion years of cosmic time. If any form of life still exists at this point, and it's hard to imagine what form it might take, it would be huddled around these last red dwarfs, eking out an existence from the meager energy they provide. Such life would need to be incredibly patient and efficient, operating on timescales that would make geological processes on Earth seem rapid by comparison. But even red dwarfs don't last forever. Let's jump again, this time to 100 trillion years in the future. 100,000 billion years, a time span that truly beggars comprehension. At this point, even the longest-lived red dwarfs will have exhausted their hydrogen fuel. The last star will have winked out, ending the Stelliferous Era that has characterized the universe since shortly after the Big Bang. The moment when the last star goes out is, in a sense, the most significant transition in the entire future history of the universe. It marks the end of an era that has lasted for 100 trillion years, and the beginning of something fundamentally different. The universe, which has been bright and warm, relatively speaking, for its entire existence thus far, enters a new age of cold and darkness. The universe has now entered what cosmologists call the degenerate era. The name comes from degenerate matter, the exotic form of matter found in white dwarfs and neutron stars, where quantum mechanical effects prevent the matter from collapsing further. despite enormous pressures. In this era, these stellar remnants become the dominant objects in the universe. White dwarfs, the collapsed cores of former sun-like stars, slowly cool and fade. When they first form, they're incredibly hot, with surface temperatures exceeding 100,000 Kelvin, making them shine brilliant white or even blue-white. But they have no internal source of heat. They're just hot, dense balls of carbon and oxygen, or helium for the lowest mass white dwarfs, slowly radiating away their stored thermal energy. This cooling process is incredibly slow. The rate at which a white dwarf cools depends on its surface area and its internal heat capacity. A typical white dwarf might take 1 billion years just to cool from 100,000 Kelvin to 10,000 Kelvin. Cooling from 10,000 to 1,000 Kelvin might take 10 billion years, and cooling from 1,000 to 100 Kelvin might take another 100 billion years or more. By the time we reach 100 trillion years into the future, most white dwarfs will have cooled to temperatures below 100 Kelvin. At this temperature, they emit virtually no visible light. They're too cool even to glow red. They would appear as black spheres, visible only by the starlight they block out or by the subtle gravitational lensing effects they produce when they pass in front of more distant light sources. These cold white dwarfs are sometimes called black dwarfs, though technically a black dwarf is defined as a white dwarf that has cooled completely to the temperature of the cosmic microwave background and is in thermal equilibrium with the universe. True black dwarfs don't exist yet. The universe isn't old enough for any white dwarf to have cooled that much. But in the degenerate era, approaching 100 trillion years, they're getting close. Neutron stars, the ultra-dense remnants of massive stars that exploded as supernovae, also cool gradually. When they first form, they're incredibly hot, with core temperatures exceeding 1 billion Kelvin. But like white dwarfs, they have no internal heat source. They're just hot, dense balls of neutrons and other exotic matter, slowly radiating away their heat. Neutron stars cool faster than white dwarfs because they have smaller surface areas relative to their mass, allowing them to radiate heat more efficiently. Within a few million years of formation, a neutron star cools enough that it stops emitting visible light. Within 1 billion years, it's cold enough that it emits only faint radio waves, and within 100 billion years or so, it's cooled to temperatures comparable to the cosmic microwave background and is essentially invisible. Black holes, scattered throughout the galaxies, present a different story. They don't cool in the conventional sense because they don't have a temperature in the usual way. But they do evaporate, slowly losing mass through a quantum mechanical process discovered by Stephen Hawking in 1974. In the degenerate era, stellar remnants dominate the universe. White dwarfs, the collapsed cores of former sun-like stars, slowly cool and fade. Neutron stars, the ultra-dense remnants of massive stars that exploded as supernovae, also cool gradually. Black holes, scattered throughout the galaxies, slowly evaporate through a quantum mechanical process discovered by Stephen Hawking. Planets, if any remain, orbit these dark remnants. They're frozen solid, their surfaces at temperatures just a few degrees above absolute zero. Any atmosphere they once had has long since frozen onto the surface or been blown away. They're dead worlds in a truly literal sense, incapable of supporting any chemistry more complicated than a few simple molecules. The galaxies themselves are beginning to come apart. Over these enormous timescales, stars occasionally have close encounters with each other. These gravitational interactions can fling stars out of the galaxy entirely, sending them flying off into intergalactic space. Slowly, over trillions upon trillions of years, galaxies lose stars this way, evaporating like water from a pond on a hot day. Other stars, through random chance, lose energy in gravitational encounters and spiral inward toward the galactic center. Eventually, they fall into the supermassive black hole at the galaxy's heart, adding their mass to it. The black hole grows larger and larger, even as the galaxy around it shrinks. There's another process that might be happening during this era, though it's highly speculative: proton decay. According to some theories in particle physics, protons, the positively charged particles in atomic nuclei, which have been stable for the entire history of the universe thus far, might not be truly stable. They might decay into lighter particles over extremely long timescales. If proton decay occurs, it has a half-life of at least 10 to the 35th years, based on current experimental limits. This is an unimaginably long time, a 1 followed by 35 zeros. But if we wait long enough, even stable-seeming protons will decay. When a proton decays, the atom it was part of falls apart. If proton decay is real, then over timescales of 10 to the 36th to 10 to the 40th years, depending on the exact proton half-life, all matter made of atoms will slowly disintegrate. White dwarfs will evaporate, their atoms breaking apart one by one. Planets will dissolve into clouds of particles. Even the largest structures will eventually crumble as their constituent protons decay. Neutron stars would decay even faster, since they're held together by the strong nuclear force between neutrons, and neutrons are even less stable than protons. A free neutron decays in about 15 minutes, though neutrons bound in nuclei are more stable. But if protons can decay, neutrons certainly can too, and neutron stars would gradually evaporate just like everything else. This process, if it occurs, marks the transition to the black hole era. In this epoch, only black holes remain as significant structures in the universe. Everything else has either decayed, evaporated, or fallen into a black hole. But black holes, too, are not eternal. In 1974, Stephen Hawking showed that black holes should emit radiation due to quantum effects near their event horizons. This Hawking radiation is incredibly faint. For a black hole the mass of the Sun, it would be trillions of times fainter than the cosmic microwave background. But it's real. And crucially, it means black holes lose mass over time. The rate at which a black hole evaporates depends on its mass. Smaller black holes evaporate faster. A black hole with the mass of the Sun would take about 10 to the 64th years to evaporate completely. Larger black holes take much, much longer. A supermassive black hole like the one at the center of Andromeda, with millions or billions of solar masses, might take 10 to the 99th years or even longer to evaporate. When a black hole finally evaporates, it does so in a final burst of radiation, converting its remaining mass into energy. Then it's gone, leaving nothing behind but a flash of light dissipating into the void. After the last black hole has evaporated, an event that might occur around 10 to the 100 years from now. A1, followed by 100 zeros. The universe enters its final era, the dark era. In this epoch, nothing remains but a dilute gas of photons, neutrinos, electrons, positrons, and perhaps some exotic particles we don't yet understand. The universe has reached a state of maximum entropy, a condition of ultimate disorder where nothing interesting can ever happen again. This is sometimes called the heat death of the universe, though it's more accurate to call it the cold death. The universe hasn't become hot. It's become utterly cold, its temperature approaching absolute zero. Energy is spread so thinly that it can't be concentrated anywhere to do any work or create any structure. The universe has run down like a clock that nobody can wind again. Life's possibilities in deep time. Throughout this journey into the far future, we've been assuming a passive role, simply watching as the universe evolves according to the laws of physics. But what about life? What about intelligence? If humanity or any other civilization survives into the distant future, might they be able to alter or escape these cosmic endpoints? This question ventures into the realm of speculation, but it's speculation grounded in physics and cosmology. Let's consider what might be possible for a sufficiently advanced civilization facing these distant futures. First, let's address the more immediate challenge: surviving the Sun's transition to a red giant. We established earlier that Earth will likely be engulfed and destroyed when the Sun expands. But this doesn't necessarily mean the end for any life or civilization that might exist on Earth at that time. The most straightforward solution is simply to leave. By 5 billion years from now, if humanity or its descendants still exist, they will presumably have had billions of years to develop space travel technology. Leaving the solar system might be trivial by that point. Alternatively, we might move Earth itself. The idea of moving Earth's orbit sounds like pure science fiction, but it's actually within the realm of physical possibility. Several proposals have been made for how to gradually nudge Earth into a wider orbit as the Sun brightens. One approach involves using gravitational assists from asteroids, carefully directing asteroid orbits so they pass close to Earth, slightly altering our planet's trajectory with each pass. Over millions of years, these tiny nudges could accumulate to move Earth significantly outward. Another proposal involves building enormous engines on Earth's surface or in orbit to provide thrust. These engines would need to operate continuously for millions of years, but they could potentially move Earth to a safe distance before the Sun's expansion becomes critical. However, both of these approaches just delay the inevitable. Even if we move Earth outward to avoid engulfment, once the Sun becomes a white dwarf, it will provide too little energy to keep Earth warm. We'd need an alternative energy source, or we'd need to move to another star system entirely. Moving to other stars is probably the more sensible long-term strategy. Even if humanity remains tied to the solar system for the next few million or even billion years, eventually we'll need to spread beyond it to survive. The good news is that there are many other stars out there, and many of them will outlive the Sun by trillions of years. Red dwarf stars are particularly attractive as potential homes for future civilizations. As we discussed, red dwarfs can burn for 6 to 12 trillion years, providing a stable energy source for an almost incomprehensibly long time. If a civilization could establish itself around a red dwarf, it could potentially persist for longer than the current age of the universe many times over. However, red dwarfs present some challenges. They're much dimmer than the Sun, so a planet would need to orbit very close to stay warm. So close that it would likely become tidally locked, always showing the same face to its star, like the Moon does to Earth. This creates a planet with one eternally daylit hemisphere and one eternally dark, which could make habitability difficult. Still, these are engineering challenges, not fundamental barriers. A sufficiently advanced civilization could likely overcome them, and the payoff, trillions of years of stable energy, would be enormous. There's also an intriguing possibility in our own solar system's near-term future. During the Sun's red giant phase, before it engulfs Earth, it will become much brighter and will heat up the outer solar system. Moons like Europa and Titan, currently frozen, might become briefly habitable. Europa, one of Jupiter's large moons, is particularly interesting. Below its icy surface, Europa has a global ocean of liquid water, kept liquid by tidal heating from Jupiter's gravity. Some scientists speculate that this ocean might already harbor simple life. When the Sun becomes a red giant, Europa's ice shell will melt, and for perhaps a few 100 million years, it will have liquid water on its surface, potentially creating a brief window of habitability. Similarly, Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid hydrocarbons on its surface. During the red giant phase, Titan might warm up enough to have liquid water on or near its surface, possibly creating habitable conditions. These windows of habitability will be brief by cosmic standards, a few 100 million years at most, but that's still plenty of time for life to potentially develop and evolve, or for refugee civilizations from the inner solar system to establish themselves. It's a fascinating thought. Life in our solar system might survive the death of Earth by migrating to the outer moons. Looking much farther ahead, to the trillion-year timescales when red dwarfs are the last stars still burning, we might ask, could life exist in such a dark, cold universe? The answer is, possibly, but it would be very different from life as we know it. Life requires energy to maintain order against the natural tendency toward disorder, entropy. On Earth, that energy ultimately comes from the sun. Plants capture solar energy through photosynthesis, and animals eat the plants, or eat other animals that ate plants, creating a food chain based on stellar energy. In a universe of dying red dwarfs, the same principle could still apply. A planet orbiting a red dwarf would receive much less energy than Earth gets from the sun, but it would receive some. Life adapted to these dim conditions might evolve much more slowly, operating on timescales of millions or billions of years, where our life operates on timescales of years or decades. Some scientists have speculated about slow life existing around white dwarfs, or even around black holes, where organisms might operate on geological timescales, taking millions of years to complete a single thought or action. Such life would be alien beyond imagining, but it might be possible. There's also the question of whether consciousness and civilization could survive the heat death of the universe. The physicist Freeman Dyson explored this idea in a famous paper titled Time Without End, where he proposed that a sufficiently advanced civilization might be able to survive indefinitely by gradually slowing down its computational processes to match the cooling universe. Dyson's idea is that as the universe cools and energy becomes scarcer, a civilization would think more and more slowly, spacing out its thoughts over longer and longer periods of time. By operating intermittently, waking up to think for a brief period, and then hibernating for much longer periods to conserve energy, a civilization could potentially experience an infinite subjective time even in a universe heading toward heat death. This is highly speculative, of course. It assumes that consciousness can be maintained at arbitrarily slow processing speeds, and that there are no fundamental physical limits that would prevent it. But it's an intriguing idea, that even in a dying universe, consciousness might persist, thinking its slow thoughts in the darkness between evaporating black holes. However, there's a darker possibility. Some versions of dark energy theory suggest that the acceleration of the universe's expansion might increase over time, eventually becoming so strong that it tears apart all structures in a big rip. In this scenario, galaxies would be ripped apart, then stars, then planets, then molecules, then atoms, and finally even atomic nuclei and subatomic particles would be torn to pieces by the accelerating expansion of space. If the Big Rip is real, it would occur at some point in the future. Different models predict different timescales, anywhere from 22 billion years to much longer. If it happens, it would represent a fundamental end to the universe as we know it, a point beyond which nothing we would recognize as physics could exist. Recent observations from DESI have suggested that dark energy might be weakening over time, which would mean the Big Rip is less likely. But these observations are still preliminary and controversial. We simply don't know enough about dark energy to say for certain what the ultimate fate of the universe will be. What we can say is that the future is not predetermined. Life, particularly intelligent life, is an active force in the universe. We're not just passive observers of cosmic evolution, we are participants in it. The choices made by future civilizations, if any exist, could shape the future of at least their local corner of the cosmos in ways we can't predict. Perhaps advanced civilizations will find ways to harness the energy of black holes or tap into the quantum vacuum. Perhaps they'll discover new physics that allows them to sidestep the limitations we currently believe in. Perhaps they'll find ways to create new universes and migrate to them. These ideas sound like science fiction, but so did space travel and computers not so long ago. Or perhaps life and intelligence are rare, brief flickers in an otherwise dead cosmos, and we are alone in facing these distant futures. In that case, the death of the last conscious being in the universe, whenever that occurs, would mark the end of the universe's ability to observe itself, to know itself. It would be a kind of final death, not just of matter and energy, but of meaning itself. Conclusion. We've traveled an immense distance tonight, not through space, but through time. 5 billion years into the future, past the death of our sun and the collision of our galaxy with Andromeda. We've ventured even farther, into a future where the last stars burn out and black holes evaporate into nothingness. It's been a long journey, and if you're still with me, if you've let these cosmic vistas wash over you as you've relaxed into rest, then you've encountered ideas that might seem overwhelming. The scale of time we've discussed is beyond human comprehension. 5 billion years, 1 trillion years, 10 to the 100th years. These numbers are so large they lose meaning. They become abstract symbols rather than quantities we can grasp. But perhaps that's okay. Perhaps the point isn't to fully comprehend these vast expanses of time, but simply to acknowledge them, to stand in their presence with a sense of awe and humility. The universe is larger and older and stranger than our daily concerns. It operates on scales that make our worries and troubles seem vanishingly small. There's a comfort in that, if you're willing to accept it. The problems that weigh on you today, the stresses and anxieties that might have kept you awake tonight, they're real and valid on the human scale. But on the cosmic scale, they're as brief and as fleeting as a single raindrop in an ocean. The universe will continue long after your troubles have passed, long after you yourself have passed, long after everything you know has passed. That might sound depressing, but it doesn't have to be. There's a freedom in recognizing your own cosmic insignificance. It means you don't have to carry the weight of the world on your shoulders. The cosmos doesn't need you to solve all its mysteries or correct all its injustices. It's enough simply to exist, to observe, to experience this brief moment of consciousness in the long life of the universe. And what a moment it is. You exist in an era when stars are still being born, when galaxies dance and merge, when the universe is lit up with stellar light. You exist in an era cool enough for atoms to exist, warm enough for liquid water, structured enough for complexity and life. In the deep future we've visited tonight, none of these things will be true. The universe will be darker, colder, simpler. We live in a special time, a golden age of cosmic history. The Stelliferous Era, the age of stars, won't last forever. But it's lasting now, and you're here to witness it. Every time you look up at the night sky and see stars, you're seeing the universe in its prime, in its moment of greatest beauty and complexity. So rest now. Let the cosmic perspective settle over you like a warm blanket. Your worries are small and temporary. The universe is vast and enduring. And you, right now, in this moment, are a part of it all. A way for the cosmos to know itself, to experience itself, to wonder about itself. As you drift toward sleep, let your mind wander through the cosmic landscapes we've visited tonight. The dying sun, huge and red, filling the sky. The collision of galaxies, stars swirling in vast cosmic eddies. The slow dimming of the universe as the last stars burn out. These images are not meant to frighten or disturb you. They're meant to put things in perspective, to show you the vast stage on which the drama of existence unfolds. And when you wake tomorrow, the sun will still be shining, middle-aged and stable, providing the energy that powers all life on Earth. The stars will still be there, scattered across the sky, each one a sun unto itself. The universe will continue its slow evolution, changing on timescales so long that you'll never notice the difference in your lifetime, or in 1,000 lifetimes. Rest easy in that knowledge. The cosmos is vast, but you are a part of it. You are stardust, atoms forged in stellar furnaces billions of years ago, now briefly organized into the form of a conscious being. You are a way for the universe to know itself. And that, on the cosmic scale or the human scale, is something beautiful. Sleep well, cosmic traveler. The universe will still be here when you wake. Thank you for joining me on this journey through deep time. If you enjoyed this voyage into the far future, please consider subscribing to the Science Pillow for more cosmic adventures designed to help you relax and rest. Sweet dreams and good night.